This video is designed to help us get through the first few sections of Chapter 5. I would like to start by directing your attention to page 170, where we have laws of exponents. These you should know from previous math classes. If you need a refresher, you could watch another video I've made called Exponent Laws. Alright, let's talk exponential function. This is our most basic form of an exponential function, and what I have here are two adjustable parameters for a and b. T is our independent variable, our domain value. When our input values are in the location of an exponent, that gives us an exponential function. Now here are some facts we should look at carefully when it comes to these two values a and b. B is the base of our exponent t, and we could consider a to be the coefficient of this expression. So let's start by talking about b. This function is only exponential if b does not equal 1. Well, let's find out what happens if we make b equal to 1. If b equals 1, 1 to any power is still 1, and we no longer have an exponential function, it becomes linear. So this is one fact about b, that in order to have an exponential function, b cannot equal 1. What else must b be? Well, b has to be positive. And the two different cases we get when looking at positive values for b are b values that are greater than 1. So let's increase the value of b. And what we're showing here are all kinds of different graphs, all of which are representing exponential growth. That's what happens when our b value is greater than 1. Let's look at the case here when b is between 0 and positive 1. So let's bring b back to 1, which creates a linear function, and now I'm going to decrease b. So when we have this second case for values of b, where b is between 0 and 1, then what we have is an exponential decay function. Let's turn b back into value greater than 1. There we go. Now a question I'll leave you with is why b cannot be negative. Now let's turn our attention to this coefficient, to a. What set of values must a belong to in order to have an exponential function? Well, a must be greater than 0. If a is 0, you get a constant function, and let's see what happens to the graph when we decrease the value of a. And this should make sense because if a is 0, anything I multiply times 0 gives me an output of zeros. And what if a was a negative? If a becomes a negative value, then what we get is the reflection of an exponential function. When b is greater than 1, we have exponential growth. When b is between 0 and 1, we have exponential decay. In section 1 of our textbook, all of the exponent problems we'll be working with will have integer exponents. This is one of the formulas that we will use for exponential growth and decay. And in this formula, remember we had f of t equals a times b to the t. This is our standard exponential function, where t is our exponent. The b value is now 1 plus r, and the a value is our initial amount. To recognize growth or decay, we'll use these inequalities. If our rate is greater than 0, there's growth. If the rate is between 0 and negative 1, there's a decay. Because in this formula, we're adding r with 1. So any positive value create a base that is greater than 1, which is an increase or a growth. And if we subtract values between negative 1 and 0, we'll have a base that is between 0 and 1, which gives us our decay. Oh, one thing I forgot to mention back when we looked at our exponential function slide. Another characteristic about a, graphically, that a is always our y-intercept, or the starting amount when t equals 0. And I can demonstrate that by increasing a. Let's look at that y-intercept. At this moment, a is 1.79. Here it's 2.37, and so on. So that is our a sub 0, the original amount when t is 0. That's also our y-intercept. In section 2, exponents we will work with will be fractions, or rational numbers. And if we have a base with a fractional exponent, p over q, if q is even, that's the same thing as having e to the p power taken to the qth root, or this is now our index of a radical. And if this is an even index, remember that we need to have a positive number under the radical, which means that b to the p power has to be positive. And here are some tips for solving problems in section 2. Sometimes achieving like bases could be helpful. So that might look like 2 to the x equals 1/8. Well, 1/8 is the power of 2. 1/8 is 2 to the negative third power. One of the laws or properties about bases and exponents, if we have an equation with like bases, then the exponents have to be equal. Another tip is that you want to try to utilize the laws of exponents to achieve an exponent 1. Let's look at this problem. 4 times x to the 3/2 power equals 32, and we're trying to solve for x. We can divide both sides by 4. Now, in order to achieve an exponent of 1, what I can do is apply the exponent of 2/3 to both sides of the equation. That gives me product of the power of a power, where I multiply exponents, and that gives me x to the first. Now this x to the 2/3 is the same thing as cube root of 8 squared, which gives me x equals 4. When we get to section 3, we'll be using our standard exponential function, but it's going to look a little bit different. This is the same exponential growth or decay formula from section 1. This will be another version of an exponential function. In section 3 on page 182 in your textbook, there's a topic called the rule of 72. Once we get to the sections about logarithmic functions and natural logs, we will examine the method for deriving this estimation tool. There will also be some half-life problems in section 3. So let's first take a look at what half-life means. Half-life is a unit of time. It's the time that it takes for a substance to decrease by half. This little table demonstrates what we mean by half-life as a unit of time. If we're starting with some amount of a substance, so if we're doing like a radioactive decay problem or something like that, at time 0 and we're beginning the problem, we have 100% of that substance. After one half-life for a particular substance, the percentage we would have remaining would be 50%. 2 half-lives, we would then have 25%. 3 half-lives, 12.5%. And you can see that as we increase the number of half-lives, we keep cutting the previous percentage in half, or decreasing it by half. When we're solving these kind of problems in our textbook, this is the formula we would use, where k is our constant half-life value. That would be the denominator in our rational exponent. B is 1/2, because what we're trying to do is find out how long it takes to get half of the previous amount. So our b value would be 1/2. A sub 0 is the initial amount at t equals 0, and t is the time taken. So again, our independent variable is t. We will get to the remaining topics in chapter 5 on a few more videos in the future. Thanks for watching and keep practicing.